All right, physics. New semester, right? We're back at this. I know that the boy, that midterm sure happened, right? That was a trip. Some people were not super affected by that. Some people were very affected by that. Some people, it was a whole mess to deal with that midterm. So, what ended up happening? If I'm sure that y'all check the emails anyway, but if the midterm helped your grade, it counts for you. If the midterm did not help your grade, it did not count for you. So basically, for lack of better term, your midterm kind of just became extra credit. It is what it is, honestly. We didn't have much control over it, right? What ended up happening there was that a cable got severed somewhere in the Northeast and cut off internet to a whole bunch of stuff, including Blackbaud, which runs my CBA. So it was completely out of our hands. There will be a separate video that goes up if you do want the answers to any or all of those questions, but I figure it might just be best right now to move right along. So, new semester, kind of like changing gears a little bit. First semester is basically all mechanics. How stuff moves, why stuff stops, continues to move, goes faster, goes slower. All that stuff was first semester. Second semester, the shift is to slightly different topics. What I'm going to start talking about today is like bare bones electricity background. And we'll get into waves a little later in the year. But for electricity, I figured I'd start like baseline stuff. We're going to talk about two and a half different kinds of electricity, kind of three types of electricity. One of them will only touch on, which is why I count it as like half, and then the other two are kind of like the big deal. Um, but you might know some stuff about electricity. You might know nothing about electricity other than the fact that it runs your phones and your computers. I'm going to try to explain, the bit of electricity that I know is like actually part of the regions and a little bit extra because I think you can handle it. Excuse me, I think you can handle it. And because I actually think it's pretty interesting. Electricity is honestly very interesting. It's the same thing as magnetism, which I really hate because I hate magnets. I hate talking about magnets. I hate studying anyway. That's different story for a different day, right? But let's start. If my mouse is in the hey, there it is. Okay. But let's just bare minimum like electricity. What is electricity? What does this mean? How do you make it? How do you store it? How do you use it? Right. So electricity is literally just the movement of charge, right? And I have to tap into chemistry here. Sorry. Happens to be the class that I teach. I know that y'all took it last year because I had some of y'all. But electricity is the movement of charge. Now, charges, last year, we learned kind of come from protons and electrons. Protons are positive. They're found in the nucleus. Electrons are negative. They're found outside the nucleus. By moving charges, you get electricity. So you might be like, well, why don't I have electricity all the time? Because there are always charges everywhere and they're moving. I should say it's like the movement of a net charge. So like this, my stylus pen does have charge, but the problem is it has equal amounts of positive and negative charge. So it has a net charge of 0. So let me kind of like make the movement of a non-zero net charge, right? If this was charged, if this had even just like one extra electron, or one fewer electron. Extra electron made it negative, a fewer electron would make it positive, and I moved it, then I would be able to generate electricity, because electricity is just the movement of charge from one space to another space. Right? The most common example of electricity, or one of the most common examples of electricity that you have seen, is not necessarily phones and computers, not necessarily man-made. It's a completely natural form of electricity. It's lightning. So like if a thunderstorm, lightning storm, you see lightning, it can go from cloud to cloud, it can go from cloud to the ground, cloud to a building, whatever, something like that. But that's electricity. That's the movement of charge. What you are seeing physically is the movement of unnecessary order of magnitude of electrons. It's electrons because electrons are actually the charges that are allowed to move from one place to another place. Although we will talk about how part of our understanding relies on a different effect. Electrons are able to move. They're on the outside of the atom, so they're kind of out here in the orbitals. When the reason that you see lightning, right? You have these clouds up in the sky, and they're raining, right? And so you get rain, blah blah blah, whatever. The ground is down here. These clouds, as they move past each other, right? They actually slide against each other and they touch, and they kind of do this kind of thing. Now, usually if I'm trying to do something like this in physics, I'm trying to demonstrate friction and heat. But in this case, I'm demonstrating the fact that because these objects are sliding past each other, they are able to transfer electrons from one to another. Now, these electrons build up, and they build up, and they build up, and if you remember from last year, these electrons are all negative, and they don't really want to be near each other. But we're forcing them all to stand right next to each other. They're gathering all in one place, right? This also happens kind of like this time of year, right? Wintertime. If you are shuffling across like a carpeted floor and you try to reach out and to open a door, you might feel the shock between your hand and the doorknob. Also might happen if you're doing your laundry, right? In the dryer, your clothes are all tumbling, they go past each other, and you try to take them out, and they're like all stuck to each other. And the reason for all of that, for all of those things happening, is some form of electricity. There's a movement of non-zero charge, right? So electrons are typically the ones responsible. They will move from one object to another. If it's the case of your laundry, they'll move from one of your pieces of clothing to another piece of clothing. One piece of clothing will be negative, the other will be positive. Opposites attract, they stick. When you separate them, as you peel them apart from each other, you might hear that little crackling, or you might see, you might actually visibly see sparks. This will also happen like if you have a fleece sweater or a fleece blanket. You kind of take it off, and you hear it, you feel it. The fleece blanket, if you've been sitting on the couch for a while and you have to get up, you take the blanket off, you'll feel it, you'll hear it. That's the movement of charge. And the reason those charges are moving, again, all these negative charges, all these electrons are hanging out near each other. They don't want to be near each other. So what do? They distribute themselves. They try to redistribute themselves evenly so that everything is balanced and everything ends up with a neutral charge again. The problem with lightning, and the reason lightning is so much bigger than the little static that you might see on your clothes, or the little static that you might see when you touch a doorknob, it's orders of magnitude more charge. These clouds are enormous, and they're transferring huge numbers of electrons from one space to another. All those electrons build up and build up and build up, and you might be like, well, why don't they just move? Why don't they just jump? Again, tapping into chemistry. We talked about this last year. Some things are good conductors, and some things are bad conductors. And depending on what material it is, the electrons can move, or the electrons could stay there, right? In the case of your hand and the doorknob's probably made of metal. If you've been building up a lot of excess charge, it wants to leave your body, but it can't just leave through any old thing. The air is not a very good conductor, but a doorknob, being made of metal, is a good conductor, has a sea of valence electrons. So you touch the doorknob, and all those extra charges go through your body and into the doorknob, where it then dissipates, and it neutralizes. I hesitate to say that word because that kind of means something else, but it kind of neutralizes your charge. Same thing happens with the fleece blanket. You've been transferring electrons back and forth, and when you take it off suddenly, those electrons have to redistribute themselves in order to maintain some balance of charge. Same thing happens here with the lightning on a much grander scale. Now, most of the time, I just said air is not a good conductor, so most of the time the lightning will go from cloud to cloud. It's very common to see cloud to cloud lightning. Usually you'll just see the sky light up. Much more rare is cloud to ground lightning. Cloud to ground lightning is rarer because it has to cross through a ton of sky to get to the ground. It doesn't want to do that. Air is not a very good conductor. These charges don't want to pass through that. So if you see cloud-to-ground lightning, particularly violent light thunderstorms, have that aspect because there's a lot of wind turbulence. There's a lot of air moving. Because there's a lot of air moving and the clouds are there, these clouds are transferring electrons back and forth, and you can get huge lightning bolts to travel from the cloud to the ground. Think about like seeing a lightning bolt. It's very rarely a straight line path. And the reason for that kind of goes actually back to earth science when we talk about rivers and the erosion pattern and how they meander and do this and that. But the reason that they go around some stuff and through other things is because water will take the path of least resistance. Electricity will do the same thing. It will try to find the path of least resistance, the easiest path for these charges to get away from each other. And I'm monologuing. There we go. Okay. Nope, we're good. I was monologuing. And what you see, like the shape of the lightning bolt that goes from cloud to ground, is actually the physical path of least resistance through the air. The air is a mixture. It's different pockets of stuff. So those charges will try to find the least resistance path. Not the shortest path, but the path that's easiest for them to travel in order to get as far away from each other as possible. Once they hit the ground, they can then dissipate into the ground. We say that it grounds itself. That grounding is a term that comes up in electrical circuitry, which we'll talk about in the near future. But just want to, I'm talking about all this. Really, I'm talking about static electricity, right? All of these things where charges are building up and building up and building up and then suddenly get released. That's static electricity. It is the movement of charge, but it happens once. And it happens because charges build up. They're still for a little while. They're static. Static electricity. And as a result of that static electricity, of that static buildup, you end up with a static discharge. The lightning bolt, the shock on the doorknob, the fleece blanket, your clothes separating, stuff like that. All right. Again, just like baseline stuff with electricity. I'm not going to give you a ton of stuff to look at here yet, because I do have to get into something else. And I know that like in class we get a little off topic here and there, just discussing stuff. If you have questions, if you're curious about like how something relates to static electricity or how something relates to electricity in general, please send me an email. I'll be happy to talk about it in one of these videos eventually. If you have questions and you're in class, obviously ask during class. But I know that for fully remote students, you don't always have that quick question answer. So please, if you have questions, if you're interested in something, I can definitely like tie it in here because I have a little more freedom to work through this because I think mathematically, I think this gets easier, and conceptually, I think this is like a much more interesting thing. I think it becomes more pertinent because of like the prevalence of phones and computers and our dependence on electricity, our dependence on information being digital, as shown by the midterm, right? So we'll continue to talk about this. Be ready. We're going to be doing a lab on C-Day. Fully remote students, you can actually do most of it on your own. There is some of it. I'm working out how you can do it. I'm trying to find a way that you can actually do all of it on your own. There's just a sheet to fill out. There is no write-up for this one, so kind of nice. There's no write-up for the lab that we're going to do on Friday. But you do need to have a good understanding of like the static electricity stuff. So we're going to talk about this for a little bit. I'll ask y'all some questions on B-Day to kind of accompany this, so that when we do the lab on C-Day, you'll have a good background for it. But please email me with questions if you have them. Please ask questions during class if you have them. I actually do like the second half of the year a little bit better. Even though I don't enjoy magnetism that much, electricity is like this crazy fascinating thing. So until next time, until either next class or next video, I will see you. Take care of yourselves. Be good, be safe, and take care, y'all.